Okay, this video is going to be on how to start some of these problems for this next week's problem set. So let's start out with number 26 here. We must apply a force of 80 newtons to move this block 2 centimeters. And then from that position, we slowly move the block. So our force does 4 joules of work. What's the block's final position? So what we're really talking about here is how much work the spring does. And although it says we move the block, so we do 4 joules of work on the spring. The idea is, and we've talked about this in class, if we're pulling this way and the spring's pulling that way, like that's our applied force and that's the spring force or something, then the work is just going to be opposite signs. So if we're pulling the block this way, we're potentially doing some positive work, and then the spring force is going to be doing the work in the other direction. So what that looks like is like the work that we do is going to be the opposite of the spring work because one's in one direction and one's in the other direction. And it's also because the block is stationary at the beginning and stationary at the end. That means there's no change in kinetic energy. Remember, work is also change in kinetic energy. So since there's no change in kinetic energy here, the work that we're doing is going to be the opposite of the work as spring's doing, and they're going to like cancel each other out for better or for worse. So what does this mean for us? That means that the work that we're going to apply is going to be the opposite of 1/2 kx initial squared minus 1/2 kx final squared. That's our formula for the work of a spring, but it's in the opposite direction. It just means we have to switch these things around. So now we know this number, because that's given in the problem, 4 joules of work. We know the initial and final positions. Well, we're looking for the final position, sorry. We know the initial position, and all we need to do is figure out the spring constant, which we can actually figure out from this 80 newtons and this 2 centimeters. Remembering that the spring constant is a force divided by a distance there. So you can figure out the spring constant here and then just plug these numbers in. The reason you're going to get 2 answers is because you've got a squared term in here, and when you take the square root, you've got a positive and negative number out of it. So there you go. Okay, moving right along, 27. So it's once again, it's the same figure 7-10. When the block is pulled out to 4 centimeters, we apply a force of 360. So right away when you're looking at this, is like, okay, I could figure out the spring constant here. Remembering to do newtons in meters and not newtons in centimeters. We pull the block to 11 centimeters and release it. How much work does the spring do on the block as it moves from x equals blah, blah, blah? So this is a pretty easy problem. This is just the work that the spring does is 1/2 kx initial squared minus 1/2 kx final squared. By the way, you can make this easier on yourself just by doing 1/2 kx initial squared minus x final squared. So you'll have the same 1/2 k in every problem. And then you're just going from +4 to +5 and block moves from, I'm so sorry. So you're starting here at +5 and then going to +3. And then you'll start at +5 and go to -3 and you go to +5 and so on and so on. So that's pretty easy to set up and do. Okay, so here's this one. This says we're given the force versus distance for the position for the spring block arrangement, same arrangement. The scale is set by, this is 160 up here. And we release the block at 12 centimeters. How much work does the spring do on the block when the block moves? So it's basically just a rerun of this problem. Only thing is now we need to figure out what the k is based upon this, remembering that the k is going to be the slope. So the slope of this line is going to give you the spring constant k. Now you're going to get a negative number for it, and I'm not totally sure what to do with that negative number for the spring constant. I should be a positive number. You shouldn't get a negative number for the spring constant. So I'm not quite sure why they have their graph going this way instead of this way. But I would say whatever number you get for your spring constant, you should just have it as a positive number. Set by, release the block at 12 centimeters. When the block moves from, we release the block at 12, x equals 12 centimeters. How much work does the spring do on the block when the block moves from +8 to +5? From +8 to -5. Okay, yeah, so it's just basically the same problem up over there. So there you go. And here comes number 34. Let me see if I can get that to focus a little better. Mildly better. So we have a brick that moves along the positive x-axis. Its acceleration as a function of its position. So this is position and acceleration. The scale of the figure is set by whatever. So this is 20 meters per second squared. What's the net work performed on the brick by the force causing the acceleration? The brick moves from here to here. So it's kind of just another spring force problem, even though it says it's not a spring, it's just a regular force. I wrote this in here to help you remember that you can find the force if you have the acceleration. So if this is the acceleration right here, you could find the force. So the slope of this thing is kind of like the spring constant, if you will. So we're looking at F equals some constant times x, even if it's not a spring. To find this, we would need to find the slope if this was a force on this axis. So what I would say is just, if you have the mass, turn this axis into a force, and then you find the slope when you're finding this thing right here. And then the work, once again, is just going to be the 1/2 k x initial squared minus 1/2 k x final squared. It's not really a spring, but we can model it just the same as we've been doing for a spring. Okay, let's look at 36. 5 kilogram brick block moves in a horizontal frictionless surface under force that varies. Oh, the figure's down here. Oh, okay, well, I think we actually did this one in class. So it's really just an area problem. If we're finding the work is just going to be the area in here. And I think we did that in class, but you can try it again. 39, so this is actually like a variable force problem that's not going to be linear. So it says this force right here equals c times x minus 3x squared, and it's all in the I direction. So if everything's happening in the I direction, it doesn't really matter that it's in the I direction. Just it's one-dimensional. So acts on the particle moving along the positive x-axis. The force is in newtons and x is in meters, and c is a constant. X equals 0, the particle's kinetic energy is 20. X equals 3, the particle's kinetic energy is 11. Find the constant c. This might be one of those problems where you're like, what the heck is going on? But I do want to remind you that work is going to be the change in the kinetic energy, right? So we know the change in the kinetic energy. Work is also going to be integral of f dx. So you Calc AB people, just might be a little bit of a struggle here. Get some help from a friend. Everybody else should be able to do this problem. So we'll be able to find the kinetic energy because it goes from this to this. And then setting up this integral over here, we're going to make an integral, and it's going to be of this function right here, cx minus 3x squared dx. Good. And then we are integrating from 0 to 3. Oh, here's the energy afterwards, 11 joules. So that's going to be equal to the change in the kinetic energy. And then you just do the integral out and you figure out what c is. So that's actually not that hard. And this last problem, the challenge problem, I think we'll just talk about it in class if we get a chance. It's an interesting problem. It's a 3-dot problem. It's got kind of a fun solution that we can work on in class. Okay, hopefully that's helpful.